Okay, welcome back to our course. In the previous lectures, we sort of discussed the fact that quantum mechanics sorts of comes in at least two equivalent formulations. One in which the wave function carries directly information about the positions, the probability of finding the particle in a given position. And another one in which the wave function carries direct information about the probability of finding a particle with a given momentum. And somehow, while in classical mechanics you have both pieces of information readily available from the state of a particle, which is a collection of positions and velocities, in quantum mechanics you can have one at a time. You can have the wave function in position representation, and then you can obtain the wave function in momentum representation through an operation, a mathematical operation called Fourier transformation. And the point about Fourier transformation that makes it the correct transformation is that it sort of seems to be preserving the product of a typical uncertainty over position and the typical uncertainty over momentum. So the typical spread out of the wave function in momentum and in position representation is the product of the typical spread outs of the wave function remains constant, which basically says that, you know, if you squeeze the wave function in position representation, you make it broader in momentum space, and if you squeeze it in momentum space, you make it broader in position representation. In this lecture, I'd like to connect this piece of information, or the possibility of having equivalent representation of the state of the system, depending on what representation I choose to use, in this case, momentum or position, is somehow reminiscent of what happens with vector spaces, if you think about it, where I have equivalent representation of my vector space depending on how I choose the basis of my vector space. I mean, at the moment, this is just an analogy. This is reminiscent of what we already know from linear algebra in a different context. And in that context, apparently I have a problem here with my computer. Apologize for being somehow in difficulty. Okay, I think I need to stop the lecture for a second. Okay, sorry. Here I'm back. So I was saying there is some kind of reminiscence with what happens with vector spaces, where I have a vector v, and I want to represent it mathematically. And the way I represent this vector mathematically is by associating to my vector coordinates, for instance, v1, v2, if this is a point of a plane. And how do I associate coordinates? Well, in order to associate coordinate, I need to specify a basis. Let me call it E1 or E2. This basis of the vector space better be orthonormal, but it may not be in general orthonormal, but we like it when it is orthonormal for a number of reasons. And then if I specify the basis, given E1 and E2, then the vector V is uniquely determined by two numbers, V1, that is defined as the inner product of V with the first vector. In this case, it corresponds to this number, V1. And V2, which is the inner product of the vector space with the second base vector, in this case, this number, V2. So This is a way I have to mathematically represent my vectors in vector space, but I can always choose a different representation. For instance, I might choose this representation, which I denote with a different e prime 1, e prime 2. So if I change representation, my vector v will be now represented by different mathematical objects. V prime 1, that is the inner product with e prime 1, and v prime 2, inner product of v with e prime 2. So why am I bringing this up here? Because I just want to build an analogy, nothing more than that. In quantum mechanics, I have two representations that seem to be mathematically different, but physically they sort of are two interchangeable ways of representing the same physical system. And there's this analogy in vector space where I have a single entity and one vector, and I have interchangeable ways of representing vector in the vector space by simply changing bases. Now, in the next several lectures, we'll see that this analogy that connects Fourier transformation in quantum mechanics to basis transformation in linear algebra is much deeper than it would seem at this first exposure. If I, at this level, I think these two systems, quantum mechanics on the one hand and vector space on the other hand, really have nothing in common. They really are two independent mathematical worlds. On the one hand, you have a world, space of functions, and a transformation between the space of functions are integrals called Fourier transform. And in this case, I have vector spaces, and the transformation between the vector spaces are changing basis, changing operations, which basically amount in this case to rotate the basis from one to another. So why should these two mathematical notions have anything in common? Well, if you think about it, this is not the first time we build an analogy between quantum mechanics and linear algebra. When we went through the time-dependent Schrödinger equation, to the stationary Schrödinger equation, we commented on the fact that the later equation, this equation, is actually a definition of an eigenvalue or eigenproblem. Where this is called an operator acting on a function. And this operator H had the property of being linear, so we define it to be a linear operator. And at that stage, we built another analogy with linear algebra that was, this is more or less like when we have a problem having a matrix and a vector, and we are looking at the eigenvalues lambda of the given matrix. So here comes two analogies between quantum mechanics formulation, mathematical formulation on one hand, and linear algebra vectors on the other hand. So something is there, and when they say 3 times is a habit, now it's just 2 analogies. I could invent stress a third analogy, but the point of this lecture is not to get to the number of analogies equal to 3, or rather emphasizes that there is some suspicious connection between quantum mechanics and linear algebra going on. And the purpose of this lecture is to sort of reveal this connection. And this operation of revealing this connection will be performed not so much for the sake of curiosity. Oh, look, I can tell you why there's this analogy between the two, but rather because based on this connection, we'll be able to sort of understand much better what a Fourier transformation is, and ultimately how to formulate quantum mechanics in a proper way. And this analogy will lead us preferential in a will lead us to defining the concept of Hilbert space in a much more digestible way, accessible way than a formal mathematical treatment would require. So I'm standing on this analogy to skip books of mathematics, essentially. That's what I'm doing. But you see what I mean in a couple of slides. So the question we want to address is, can quantum mechanics be formulated in terms of linear algebra? That's the question we would like to address. So forget about operators and functions. Can we reformulate everything in terms of matrices and vectors? Because if you could do that, then things would be so much easier. And in order to make steps into that direction, I'll introduce something that is called lattice discretization. Okay, suppose, what is lattice discretization? Lattice discretization is a way to approximate a continuum problem by means of a sufficiently fine-grained discrete problem. How? Well, let's see. Suppose we have a wave function that describes a physical system. Maybe we want to compute this wave function. Maybe we already have this wave function. Let's suppose for a moment we already have the wave function. Now we know that the wave function must be normalized, right? It must correspond to a finite probability to find a particle somewhere. So the wave function might be localized in a particular region of space. If it wouldn't go to 0 here and here, then of course the integral from minus infinity to plus infinity of the square of this function wouldn't be finite, it would be infinite. And so the function would not be normalized. So we know that it's going to go to 0 pretty fast as I move right and left along the x-axis, because otherwise the system with this wave function could not represent the probability. So there's going to be a maximum and a minimum position beyond which the wave function is so small that I cannot even bother considering. The probability is so small that basically I can neglect it. I decided when, maybe if I want probability to be less than 1 part per mil, I stop here. If I want 1 part per 10,000 mil thousands, I will stop maybe here and here. But I set the accuracy and I can check, whenever this integral is going to be almost 1 up to a small difference that is small enough, I'm going to stop. So let's say I stop here. That's the first approximation I can always do, and it's a controllable approximation in the sense that it is, I can make it as accurate as I want by going larger and larger. Now let me do a second approximation, and let's divide the position between x min and x max into a final set of lattice points. What do I mean by this? I take this and I chop this distance into a set of little beans, and I assume that I take these beams so fine-grained, so close to each other, that the function can be considered almost constant within the beams. So for instance, here, the function is basically constant, here, here. I can take the function to be the value of the function at the beginning of the beam, for instance. Now you see, I've represented this function with this set of assuming that it's constant within the beam. Now, clearly, in some points in this specific example, this approximation was not very good. For instance, here, clearly the function was not constant within the beam, and neither was here, for instance. So maybe in order to get a more accurate approximation, I need to take twice as many beams. Now I'm not going to draw this for twice as many beans, but you know, if I use more and more beans, let me just erase this and picture what's going to happen when I use many beans. What I'm going to get is going to get a stepwise representation of my original function. I don't know exactly how it looked like because I erased it, but I'm going to get a very accurate stepwise representation of this function. And I can do that until I'm happy that my representation of the wave function is actually a good one. How do I know it's a good one? Well, typically, when the typical length scale over which the wave function changes is comparable with the lattice, but the lattice spacing is chosen much smaller than the typical length over this function changes. For instance, I would say this function is changing over this length, and therefore must use lattice spacing that are much smaller than that to accurately describe this decrease of the function. Because if I did not, and I choose lattice spacing much larger than that, for instance, one big lattice spacing like this, I would approximate all of this structure with a constant, which obviously would be a very bad approximation. Now, the point that I want to make is that I can make this approximation as accurate as I want by choosing sufficiently many points. That is, by discretizing using a sufficiently fine-grained spacing lattice, grained lattice. Maybe I need twice as many, 4 times, 16 times as many points, but eventually I get the accuracy I want. So it is an approximation, but it's a controllable approximation. I can always make it better by adding more points. And after I'm done, my function, psi of x, is reduced to a set of numbers. What do I mean? If I want to specify what function I am, I have to specify an infinite amount of numbers, if you think of it. I have my function to tell you exactly what function I'm looking at. I have to tell you what is the value of the function in each point from x minimum to x maximum. Right? If I want to really specify a function in continuous space, I need infinite many numbers, with each number being the function in a particular position f of x. Give me x between x minimum and x maximum. And I need to tell you what is the value of psi of x. That's what is a function. Give me x and tell me what it is assigned to it. So these are infinitely many operations that I need to do to completely specify the function. Now, after I lattice discretize, all I have to do is to tell you what is the function. I have, introduced an index that tells me where I am on the lattice. Maybe this is e equals 0, e equals 1, e equals 3. And all I have to do to specify the function is the value of the function at that index. For instance, this is I equal 6 of 5, and this is 5, 5 of psi 5. This is psi, whatever it is, 9. So after discretization, a function is completely specified by a set of numbers, phi 1, phi 2, phi 3, phi n. This is phi n. Okay? So if you give me this set of function of numbers, I know within this lattice discretization what function we're talking about. This is a vectorization, if you want, of the function, translating a function into a vector. You see, I'm building the analogy with the vector space, associating to a function a string of numbers, which basically look like coordinates of a vector. Now, but if the function become numbers, vectors, what is an operator becoming? Right? Because remember, quantum mechanics is defined by a Schrödinger equation. Now, this guy, after discretization, becomes a vector, which can represent also with this notation, if you want, the vector notation. By vector notation, I mean collection of coordinates. But these coordinates are not x, y, z coordinates. Careful. These numbers, which specify this vector, have nothing to do with the Cartesian coordinates, because we are not in n dimensions. These are n numbers which I use to approximate the value of the function in n points of my grid. This is psi 3, this is psi 4, this is psi 5, and so on and so forth. Okay. Now I want to look at, after discretization, I want to look what the Hamiltonian of any differential operator becomes. Okay? Well, if you think about it, the operator takes a function and gives me another function. Well, if this function is an eigenstate, all it will do, it will stretch by the eigenvalue of the function. But in general, the operator acting on a function that is not an eigenfunction of that operator will produce a different function, which means that in general, h psi will be a function of, I don't know, psi. And again, psi of x can be associated to a vector on the grid, which specify the value of the function in each of the points. So we see that the Hamiltonian, after discretization, will be a linear operator that transforms a vector into another vector. What is the mathematical objects that transform vectors into vectors in a linear way? Of course, it's a matrix. So we expect the Hamiltonian to be represented by a matrix after discretization. Okay? So how does the matrix look like? In order to do that, let's begin by considering the simplest case, which is the free particle. Have a two-well derivative. So let's look how the free Hamiltonian acts on the particle. Well, what this will do, it will take the function. Well, let's first say, first we notice that the second derivative is nothing but the derivative of the first derivative. So this will take the function c of x. It will add the function. It will move the function by the amount delta x and subtract the function. That's the definition of the discrete derivative. Now, this is after discretization, and delta x is precisely my lattice spacing. So just to summarize what I'm saying, in the continuum, I have to take the limit of these objects for delta x going to 0, and this will define the derivative. But if I put things on lattice, I cannot take the limit delta x going to 0 because the smallest distance I can resolve is precisely the lattice spacing delta x, and that must remain fixed. So on a lattice, after discretization, taking the limit delta x going to infinity to 0, it is equivalent to letting delta x being the shortest displacement on the lattice. Okay? So if I do this again, I take the derivative into different points. For instance, the derivative at x minus the derivative of x minus delta x. So if you do that, you get sine of x plus delta x minus sine of x. Now I take the difference between the derivative evaluated in x minus delta x. So this is going to be the derivative at x minus the derivative, for example, is x minus delta x divided by delta x. That's the second derivative, right? So if I do that, I will get this minus sine of x plus, I have to write things in a more compact way if we can stay on the line. This is going to be psi of x plus delta x plus psi of x minus delta x minus twice psi of x. If you work out this difference, you'll discover that that's exactly what comes out. Delta x squared. So that's what a discretized derivative will do. But now if I translate this in matrix language, what does it mean? It means that if I give the function, anytime you see a coordinate psi, I, what this operator will do will take psi I at the next index. So let me take this out of the game. It will be psi I plus 1, because you see I'm looking at the next index, moving to the right, plus psi I minus 1, minus 2 psi I, and I put the delta x square here. So you see I'm taking a linear combination of components of my vector. And that's what a matrix vector multiplication is doing, right? They're generating linear combination of components. And you do this for each I. So if I were to write this as a matrix, my action of H on psi is basically a matrix that looks like this. These are I'm putting in column all the positional, all the discrete points that define my function. This, psi, psi 2, psi 3, psi 7, psi 9, and so forth. I'm putting that into a column. And now look at here. Here is negative h bar squared over 2m delta x squared. Delta x is precisely this distance here. And now if I look, how does this matrix look like? I think you can convince yourself pretty straightforwardly that this is basically minus 2 here on the diagonal. And this is the part that comes from this, because this is the diagonal part of the transformation. Take the vector I and just put minus 2 times I. But then I have to add the value of the function one step up and one step backwards. So basically to this, I take this point, say this is a psi I. I take my negative of this and I add psi I plus 1 and psi I minus 1, which are respectively this point here and this point here. So I have 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. So I have a band diagonal structure and 0 everywhere else. You see, if you're not convinced, let's look at the if row of, so h times psi is going to be a vector, right? And this will have n values. We get an index k going from 1 to n. Let's look at how much this vector looks like, say, at the specific, I don't know, the fifth, k equal 5, the fifth point, 1, 2, 3, 4, 5. So I could take the matrix row multiplication. This is going to be 0, 0, 0, 0. When I get to 4, I will get psi 4 times 1, negative 2 psi 5, plus psi 6, and then get 0, 0, 0, 0, 0, and I continue the multiplication. And then I'll have to multiply with a negative h bar square over 2m delta x squared. And that's precisely the definition of the second derivative of the function at the position identified by the label I equal to 5. Right? So we are getting to see that the kinetic energy, the action of the kinetic energy Hamiltonian on the wave function after discretization is completely represented by this matrix, which is basically the discrete representation of the double differential operator. So differential operators can be translated into matrices. That's the big message after you perform discretization. Okay, so now let's look at the rest of the wave function. The rest of the wave function is the discrete representation of this part. Now, after I translate this into indices, I have that this function u of x is represented by a set of indices, u and I, which is the indices, the values that represent the value of u, the function u, on the same lattice. And this is basically psi I. So if I add this to the previous part, I will come to this following conclusion, that if I have now the full Hamiltonian, and I look at the ith vector, right, and I represent this as a matrix vector representation, there will be the sum of two contributions there would be a term which will look like this on the main diagonal with a 2. So I will have to erase this. And there will be a plus because there's a negative 2 on the diagonal. But on top of that, there will be a function u1, the diagonal term that comes from the potential. uk, this is the kth index, and this is the n index. But the potential will only enter in the diagonal term. Off diagonal, there will be only the kinetic energy. And everywhere else is full of zeros. Okay, so this is the structure of the Hamiltonian. So even though you're not, I'm not asking you to remember exactly how you represent a Hamiltonian in discrete lattice. You can consider this more like an exercise to be able to write down the correct metrics given a Hamiltonian. But we will use this in an exercise we will look at in the next lecture. But the point that I want to make here is that the analogy between the Schrödinger problem that we derived and the linear algebra problem that we speculated to be sort of similar to it can be made explicit by performing lattice discretization. In other words, a lattice discretization turns a functional eigenvalue problem into a discrete eigenvalue problem. So we have built the connection between quantum mechanics and linear algebra at the level of the Schrödinger equation. So what is the connection between linear algebra and quantum mechanics at the level of a Fourier transformation? Remember, I have my wave function in position space, and I want to find a wave function in momentum space. And I sort of speculated before that this is a little bit like when you change vector bases in the vector. You change the basis set for a vector space. So let me remind you that in linear algebra, you can always define a vector change of basis operator through a unitary or an orthogonal matrix, right? And given an orthogonal matrix, you can represent the new coordinates so remember, I have my set of coordinates v1 and v2, and I want the set of coordinates v1 prime, v2 prime, and which are the set of coordinates, sorry, let me say it again. I have my set of coordinates in my original basis. So I have my vector space, I have an original set of bases, e1 and e2. I have my vector v. My vector v in this base will give me two components, v1 and v2. I want to change base in a different base, maybe this one, e1 prime, e2 prime. And I want my new set of components in this new basis, which I will call v1 prime and v2 prime. The new components are obtained from the product component through a matrix, which in this case is a rotation matrix. Okay, so basically it tells me the Vk prime is the sum over L of OKL VL. This is an orthogonal matrix. And you should have covered this material in the statistical computing course. I will go over it again later on in one of the lectures that I give on mathematical formalism. But for the time being, just to, let's just remember that going from one vector space to another is a change of basis. So the basics are changing the basis in vector space involves multiplying the components for appropriate matrices, right? So now I took the pain to go through all this to like to convince you that the Fourier transformation is nothing but a change of basis in the space of function we were discussing. How come? Well, look, I have my tilde function. The tilde function is obtained is a function of p, right? And this is an integral over e to the negative I h bar p dot x, my original function. Okay, now this is an integral. But if after I've done discretization, this integral of my function can be, represented as a discrete sum. That's the Riemann decomposition, the Riemann's definition of integral, right? You turn your integral, you approximate it with the sum of delta x f of xi, right? That's the approximation for integral in dx of f of x, right? All I want to emphasize is that this basically amounts to a matrix vector multiplication after discretization. In fact, after discretization, I can assign an index to my momentum components. So let's call it psi tilde k. And if I discretize this integral, I can reduce it to a sum, right? We all know that this is a sum. And so I'll have my value of the momentum k, pk, which is the particular label in momentum, index of momentum I'm interested in computing. See? And this will be whatever it is, it's the position of my functions, and then I'm a summing of functions. So basically, what this is the function at pk, which is the particular value in the discretization of momentum p minimum to p maximum, and I'm interested in pk, which is somewhere here, is obtained from a sum, and I have two over basically my vector with a particular linear combination, right? Which comes from these phases. So if I look at this as a matrix in space k I, this is really that psi tilde k is equal sum over I u k I psi I. Because this object I'm summing over has two indices, I, which refers to the position I'm picking up, and k, which refers to the momentum that I want to calculate. And I'm summing many of these, one for each I, with a particular combination. That's nothing but a row column multiplication, which is the heart of this matrix multiplication. So all I want to emphasize with this is that after discretization, changing from momentum representation to coordinate representation to momentum representation or back, in other words, performing a Fourier transformation, basically amounts to changing a basis in the vector space that describes the state of the system after discretization. So for each state, I have a wave function, fix the basis. If I'm using the position basis, I have the position state wave function. If I want to go to the momentum basis, I have to rotate to transform that basis. And rather than using a rotation matrix, you use this phase matrix, which defines the Fourier transform. So the analogy that I was building before that, in vector spaces, I have something similar that I can represent the same vector in different bases and go from one to the other one, is actually made explicit by discretization by considering momentum space and position space as different bases of my space of functions. So this essence of this lecture is really that of giving you this idea that although spaces of functions are more complicated than spaces of vectors, you can turn the one into the other by performing lattice discretization of space. And if you can do that, then you can basically turn the mathematics of quantum mechanics in terms of a mathematics of linear algebra, which is a discrete mathematics, much easier to solve, and most importantly, something that computers can do very, very, very efficiently. We will use this analogy not so much as a tool for making calculation, but as a tool to arrive to define the main rules of quantum mechanics by building an analogy with what happens in vector spaces. So I urge you to familiarize with concepts in linear algebra, because they must provide this easy to understand version of concepts in quantum mechanics. And you can go from one to the other. You can make this transition very explicit by performing lattice discretization. Okay, I think that's it for today.